When we're looking at forces, we want to be able to keep track of the different forces on an object, and then that can help us see how that object is going to move. So we have two tools to help us with that. We have system diagrams. And system diagrams are a quick sketch of the object that we're looking at in the question, and we're going to include any other objects that are interacting or touching it, and we'll make a list of all the forces when we do the system diagram. The other type of diagram we're going to use to keep track of forces is a free body diagram. In the free body diagram, we'll sketch only the object and the forces acting on this object. And in the free body diagram, usually we show the object as either a box or a dot, a small circle. And then we show all of the forces coming from that box or dot. So let's look at some examples on how to do these. And it does just take practice on drawing both the system diagrams and the free body diagrams, and they get easier with more practice. In our first example, we're going to look at a bird that's standing on a branch, motionless. So right off the bat, if I see an object that is at rest, so in this case that object is at rest, or if it's moving at a constant velocity as well. So this isn't the case here, but sometimes that you might see that as well. We know the forces are balanced. So this V with the arrow means velocity. So if I have an object at rest or moving with a constant velocity, and the constant velocity means that it has the same speed and the same direction. So if I do have this constant velocity or at rest, in this case my bird is at rest, what that tells me is that there's no unbalanced force acting on the object. So when we get to our free body diagram, this will just give us a bit of information, but it's good to tie in Newton's first law, which tells us that the object will continue on at rest or at the same velocity and have constant velocity if there is no unbalanced force acting on that object. So we're going to keep that in mind. So the first thing I want to do is to draw a sketch of this bird sitting on the branch and list the forces. That's my system diagram. So I have my system diagram, and I will admit I'm not an art teacher, so my system diagrams are going to be a little bit rough. And what we want to do is look at that bird, and we're going to think of all the contact forces that are on the bird. So we want to see what it's actually touching and what contact forces we have, and we also want to look at the non-contact forces. So the only thing this bird is in contact with is this branch. So, and the non-contact force would be anything acting on it. I like to just keep in mind a list of the possibilities. And then I can go through the list and see which of these forces apply to this situation. So I like to actually start with gravity, and it's always a non-contact force. So I'm going to list that first. And the force of gravity is always of the earth on my object, which is the bird. So when we list our forces, it's good to say what they're on. And then I keep going down the list. So normal force would hold it up against gravity. Sometimes we have an applied force where it's pushing. They're both contact forces resulting from a push or holding up. So we definitely have that. This branch is holding the bird up. I'm going to list that one as well. So the normal force is of the branch on the bird. So we're always looking at the bird. So we should always have it that it's on the bird. And then I'll keep going through my list and make sure I've got all the forces. Friction, that would only be if the bird was moving and there was resistance. It was stopping it from moving. So when you push something, there's friction that slows it down or resists its motion. Tension is when we have a rope or a string, and that's not the case. We already have gravity. Springs would be when you actually have a spring or an elastic, which we don't have. An electromagnetic force, we don't have either. So out of all our forces, these are the only ones. We also have air resistance as a possibility, not in this case, because again, air resistance is when things are moving and it's the resistance of the air to the motion. Once we have our system diagram, then we can draw our free body diagram, and we're going to just put these forces on my free body diagram. So we draw the object either as a box, you can also do this as a dot, so I'll do both cases. The textbook and online materials all use the box, so we'll mostly be using this box. And in this case, I only have to put 2 forces on my free body diagram. So some key things about the free body diagram, we always start the force at the box or the dot, whichever one you're using, and it goes in the direction that the force is moving. So remember, forces are vectors because they have a direction and we can draw them as arrows. So my force of gravity I like to start with because it's always, the force of gravity is always down towards the center of the earth. So I'm going to put that on both methods of doing a free body diagram. So I started at the box and then go down, or on the dot and go down. And I can label this as my force of gravity in either diagram. The next thing that I need to put on is this normal force. And I'm going to, again, start it at the box and show where it's going. If gravity is pulling the bird down, the normal force is balancing it out so that it stays still. That's why when you're sitting on a chair, you don't fall through to the center of the earth, because the ground or the chair is holding you up. And the same with this bird. It's not falling because the branch is holding it up. And we'll show that as our normal force in the up direction. So the key things here are to draw just your object. This is like my bird. You can represent it as either a box or a dot. And then show all of the forces that you listed in your system diagram on coming from that object and going in the direction that the force will go in. And you also have to label those forces. So you do the box, draw your forces starting from the box, and put in your labels. One last thing that we're going to do, because it will help us with our next lesson, is if we have an object that is either at rest or moving with a constant velocity, that means that same speed and the same direction, we know that there's no unbalanced force, or we could also say that the forces are balanced. So that means there's no unbalanced force that's causing this bird to move. That means both of these forces have to be balanced. There's an equal pull in both directions between gravity and the normal force or push, so that the bird is not going to move one way or the other. So you kind of can think of this like a tug of war. The force of gravity is pulling down, the normal force is pushing up, but because there's an equal push and pull, the bird is not going to move. It's going to stay motionless. And this is a key concept for this unit. When those forces are balanced, that object will not move. So the last thing that I like to do, just because it helps us when we're doing other questions, if you have that bird not moving or object not moving, if you're doing another question, you want to show that these forces are balanced and they're an equal push and pull. So we draw a line to show that they're the same length or equal. And I can do this on both, no matter which diagram I am using. So that's my free body diagram. It seems like a lot, but it gets easier once you've done a few. So let's try another one. In my next example, I'm going to have a curling stone that's gliding along the ice with a small amount of friction. So we'll start with our system diagram, and then we'll do our free body diagram after we have that system diagram. And I just kept our list of forces that might be affecting my object so that we can list them out. So I'm just going to do a quick sketch of a curling stone gliding across the ice. So I have my curling stone. I drew these lines to show that it's moving to the right, so it's like the trail. The lines show the trail of the curling stone. So we want to start off, once we've done our system diagram, by listing the forces, and we're going to list contact and non-contact forces. And we'll just go through my list of possible forces and put the ones that apply here. So I actually like to start with gravity, so I'll list that one first. Gravity is a non-contact force, so I'm going to put it under the non-contact. And gravity is always of the earth on whatever object we're looking at. In this case, it's the stone. And then I can go through my list and see what else I have affecting this stone. So I have gravity. There's also possibly a normal force holding it up, and a applied force if there's something pushing it. There's nothing pushing this stone, it's just gliding. So, but there is a normal force holding it up. So this normal force will hold it up from gravity, and this applied force would be a push or also a pull by an object. So let me just write that normal force. What is holding it up and stopping it from going towards the center of the earth from gravity? That's the ice underneath it. So we do have the ice underneath it holding that curling stone up. So I'll list that the normal force is of the ice on the stone. So I can keep on going down my list. I've got my normal force that's holding it up, no push. Friction. There is friction present because it tells us in the question. So they usually should give you a hint. Sometimes in physics we assume there's no friction, but sometimes we will take it into account, and they did tell us in the question we want to include friction. So we'll list that. Friction is always a contact force because it only happens when surfaces are sliding across each other. So force of friction, and that's going to be between the two surfaces. I have the ice and the stone are my two surfaces. So it's actually of the ice on the stone. And you'll always see, because friction occurs where there is a contact, that there should be a normal force and a force of friction between the same two objects. Let's keep on looking at our forces and see if we have anything else. Tension, there are no strings here, so no tension. We already got gravity. Spring force, there is no spring force because there's no springs. Electromagnetism, no. And we don't have anything that's a magnet or a charged particle. And air resistance, we could put it in, but since they didn't tell us to, I would assume that there's no significant air resistance. So we're going to leave that one out unless they tell us to include it and to take into account the air resistance. Often it's so small that we don't include it. So once we have that, we can start our free body diagram. I'm just going to do the box version for this one. So this box is my stone. I'm a big fan of the free body diagrams because it doesn't involve drawing. And we want to list all of these forces, draw them on as arrows, starting from the box and going in the direction that the force acts. Gravity is a good force to start with because it's always down towards the center of the earth. So I draw it on and label it. The normal force is holding up the stone. It's always going to be perpendicular to the surface. So since the surface is flat, the normal force will be perpendicular or at 90 degrees to the surface. So the normal force will be up. And then we have one more force, and that's the force of friction. Friction's always going to be in the opposite direction to the motion. So if this is moving to the right, friction's going to slow it down and resist that motion. It's going to be to the left. So if it's moving to the right, friction will be to the left. So my normal force would be perpendicular, and friction's always going to be opposite to motion. So we'll draw that force in going backwards. So right off the bat, you should notice that the forces are not balanced. We can't have a equal tug of war. But what I like to do is look at the tug of war in both the horizontal and the vertical direction. So in the vertical direction, the stone isn't changing its motion up and down. So these must be equal for the rock not to be moving up or down. So they're balanced. It's not flying up into the air, it's not falling into the earth. But in the horizontal, the stone is going to be changing its motion. So it's moving forwards, but it's going to be slowing down because the force of friction is like resisting its motion and slowing it down. So we're going to start to look at this free body diagram as telling us what's happening to the motion. And we want to keep that in mind whenever we're doing a free body diagram. Let's try one more, and then you can try a few on your own. In this problem, we have a toy that's being dragged horizontally by a child holding a string, and it's being pulled at a constant speed. And the problem also tells us that we want to include friction. So let's start off with our system diagram where we just sketch the situation. So we want to show the toy. I'm just going to assume it's a wagon on wheels or something on wheels. And it's being dragged along the ground horizontally by a child. And that is my basic sketch. I want to look at what forces are present, both contact and non-contact, so that I can do my free body diagram with those forces. So let's go through the list. I'm going to start with gravity again, and we're only interested in this toy right here. That there are going to be lots of other forces, but we're going to look at the forces on the toy. So just the force of gravity of the earth on the toy. What other forces are acting on the toy? Let's check them out. We could have a normal force that's holding it up. That normal force is what holds it up. Or an applied force of a push or a pull of an object that's in contact. And there is a normal force holding this toy up. It's not falling. It's being held up by the ground. So that's my next force, is that normal force of the ground on the toy. I don't have an object in direct contact pushing or pulling, but I do have a string, so we're just going to wait because the string will be tension. Is there friction? It does tell me in the problem that we have to consider friction. Sometimes if it's very small, we can neglect it and say it's so small we don't need to worry about it, but in this case it told us in the problem to include friction, so I want to include that. The friction is going to be between the ground and the toy as well. So that's going to be the friction of the ground on the toy. And we'll keep going down our list. Do we have tension? Yes, there is a string. So we have the force of tension. There is a rope here, or a string, and there's a child pulling it. I like to say that it's not the string that's pulling on the object, because strings can't actually move and pull in and of themselves. So it's the force of the tension of the child on the toy, because that child is pulling the string. And we'll just double check all the other forces. We've got 1, 2, 3, 4. We're on the spring force. No spring force, no springs here. Electromagnetic force only occurs if there's charged particles or something magnetic, which is not in this case. And then lastly, the air resistance. Since it didn't tell us to include air resistance, we're going to assume there's no large amount of air resistance, so we won't include that force. Once we've listed our forces, now we're ready to put them on our free body diagram. So we'll have to include all 4 of these, and we're interested in the toy. So I like to start out of all of these forces with gravity, and then I also like to do the normal force that's holding it up. So we have our force of gravity, pulling it down, and then the force of the floor on the toy. It should always be perpendicular to the floor, and that would be up. And I also like to, right off the bat, if I notice that toy's not moving vertically, it's at rest vertically. It's moving horizontally, but it's not moving up or down. It's at rest vertically. That tells us that the push and pull in the up and down direction here of these forces have to be equal. So I just do a little mark that they're equal. My forces are equal in the vertical because it's not moving up and down. Then I can do my last 2 forces. So the last 2 are the tension and the friction. And I have the person pulling to the right. So friction's always going to be opposite the motion. So friction will be going backwards, and the tension is pulling to the right. One more thing that I notice is that it's going at a constant speed, and it's going in the same direction. So that means it's going at a constant velocity. So I know that this force going backwards and this force going forward must also be balanced. If it's moving at a constant velocity, it's not causing a change in the motion. So my force of friction pulling backwards and the force of tension pulling forwards is equal to each other. Since I already used a 1 dash, I'm going to show that these are equal to each other, but not necessarily the same as these ones going up and down. So they're equal in magnitude. I just put a double dash on them. So that's because if the object is constant velocity, forces are balanced. This can be a tough one to think of because we often think if it's moving, there's something causing the motion. It's moving forwards. And that's because we're used to friction slowing things down, so we always have to pull to get things to move with a constant speed. But once you have something moving, it will always go with this, it will always move with the same speed unless there's an unbalanced force. So if I didn't have something pulling it and there was just friction, it would slow down. But if I have something pulling with equal force, then it's like that tug of war is balanced, so they're going to continue on with the same motion. So those forces are balanced. We'll talk about this in our next lesson. So if you're not sure about these dashes, then we'll discuss that further, but it's very good practice to start putting them on to show that the top and the bottom are equal because it's not moving up and down, and that the two forces forward and backwards are equal because it's not speeding up or slowing down. An unbalanced force will cause the object to either speed up or slow down. And that's actually our next lesson, which is Newton's second law. There are some practice questions to try and some answers for you after this. So you can check out the next part of the lesson for those.